Dr. Esther Trufan, and in this video, we're going to explore the ideal gas law. By definition, most gases can be considered ideal under specific circumstances, and those include low pressure, and the 1 atmosphere or 1 bar are considered low pressure. This is the regular atmospheric pressure in most places. High temperature is also considered to lead towards ideal behavior in gases, and are 298 Kelvin or 25 degrees Celsius room temperature is under most circumstances considered high enough temperature for most gases to behave ideally. So that means that every time in the chemistry lab, if you were working with gases, then you can assume ideal behavior for all of them. The ideal gas law tells us that pressure times volume equals number of moles times a gas constant R times temperature, and this temperature will have to be expressed in Kelvin because it relates to the absolute temperature of the gases. The value of R, depending on which textbook source you're using, it can be 0.08206 liters times atmosphere over mole times Kelvin, or it can be 0.0831 liters times bar divided by mole times Kelvin. And you'll notice that the value of R will greatly depend in the units in which your pressure is expressed. For the popcorn experiment, the volume of the popcorn, or the volume of the gas, is going to be the volume of the kernels. And we determine this by displacement of water inside a graduated cylinder with some number of popcorn kernels. The mass that we're using here is going to be the mass of the water that evaporated in the process of popping the corn. So first we had the mass of the Erlenmeyer flask and the mass of the popcorn kernels and the mass of the oil that was added. And at the end of the experiment, we had the mass of the Erlenmeyer with the mass of leftover popcorn and the mass of potentially oil residue. The difference in the two masses was the mass of the water that was evaporated. And this is what we're using here for the mass of the gas. In this case, our gas is the water vapor. The number of moles will then be calculated using the mass, and we can go ahead and say if we have 0.75 grams of water, then each 1 mole of water weighs 18 grams. And from there, we can find that the number of moles is 0.0417 moles. And this is how many moles of gas we have available. We have the R value, and we have the temperature at 240 degrees Celsius. This is what we consider the boiling point of the oil in which the experiment was conducted. The task is for us to determine how much pressure could potentially build up inside the popcorn kernel before it pops. And for that, we can use our expression. Let's make sure that everything is in the appropriate units. We will need to calculate pressure. And if our R value is expressed as 0.08206 liters times atmosphere over mole times Kelvin, then our final answer for pressure is going to be in atmospheres. The volume will have to be expressed in liters. And if we have 4.13 milliliters, then this will need to be converted into liters. 1 milliliter is the same as 10 to the negative third liters, giving us 0.00413 liters. The number of moles we just calculated, the value of R is present, and the value for temperature is provided in units of Kelvin, which is the 513 Kelvin. And now let's derive the value of P. P equals N times R times T divided by volume, because we divided both sides of this equation by our volume. To calculate the pressure, we will place our numbers in the right position. The value of N is 0.0417 moles. The value of R is 0.08206 liters times atmosphere over moles times Kelvin. And the temperature is 513 Kelvin. The whole thing gets divided by the volume expressed in liters, which is 0.00413 liters. Completing the equation, we find that the liters will simplify, the moles will simplify, and the Kelvin will cancel, leaving us with units of atmosphere as anticipated. The number that will indicate how many atmospheres of pressure built up inside our popcorn is 425 atmospheres, which is a lot considering that a regular soda bottle will explode somewhere around 50 to 70 atmospheres. A popcorn kernel can resist up to 9 times that much pressure. Another gas-producing reaction is the reaction between magnesium solid ribbons and hydrochloric acid solutions. The result of this reaction is going to be hydrogen gas. Now, this hydrogen gas can be collected over water or it can be released in the atmosphere. However, we can use the ideal gas law to calculate the approximate volume of hydrogen gas, so we may choose the appropriate graduated cylinder in which to collect. Here is the information that we have available. We have our temperature as 25 degrees Celsius, which converted to Kelvin will be 298 Kelvin. We also have our pressure provided as a 1.2 atmospheres, and we can keep it as such as long as we're using the R value that contains the atmosphere in it, which is the 0.08206 liters times atmosphere over moles times Kelvin. And then we know that we have a mass of magnesium of 0.10 grams. From the mass of magnesium, we should be able to determine the moles of the gas that we anticipate to form. So we begin with the 0.10 grams of magnesium. In step 1, we convert from grams of magnesium to moles of magnesium. Each 1 mole of magnesium weighs 24.3 grams. And from there, we're going to say that for every 1 mole of magnesium consumed in the reaction, we're producing a 1 mole of hydrogen gas, giving us a final number of moles of gas of 0.004115 moles of hydrogen. We have the moles, we have the temperature, we have the pressure, we know the constant. We can estimate the volume of the hydrogen gas. So if our original equation is PV equals nRT, if we divide both sides by the pressure, then our volume will be equal to nRT divided by pressure. So let's plug in our values. We have number of moles, 0.004115 moles, times our constant, 0.08206 liters times atmosphere over moles times Kelvin, times the temperature in Kelvin, 298 Kelvin, divided by the 1.2 atmospheres. The volume that we calculate this way is going to be 0.086 liters, which if we convert to milliliters, we get 86 milliliters, which means that the ideal instrument to collect this gas, if we want to know the exact volume that is produced, would be a 100 milliliter graduated cylinder. And we have to keep in mind that every time we collect a gas on top of water, then we need to add a little bit of room for the extra water vapor that will be also part of the experiment. Another experiment that works with the generation of a gas is the reaction between the sodium bicarbonate and vinegar. And here is the chemical reaction associated with the process. The sodium bicarbonate is the baking soda and the acetic acid is the active ingredient in vinegar. If we know the mass of the sodium bicarbonate, we should be able to determine the number of moles of gas produced in the process. So we start with 4.60 grams of sodium bicarbonate. We're going to convert in the first step to moles. 1 mole of sodium bicarbonate weighs 84 grams of sodium bicarbonate. Then in the next step, we're going to say that every 1 mole of sodium bicarbonate that reacted in this process will produce 1 mole of carbon dioxide. This will result in the formation of 0.0548 moles of carbon dioxide. So we have our N value. Next, we're going to look at our temperature value. It says 40 degrees Celsius, which converted to Kelvin will be 313 Kelvin. We have our pressure. It is 0.75 bar, which means that the constant that we will have to use is the 0.0831 liters times bar divided by mole times Kelvin. And then finally, we need to find the volume. So we don't know what that is yet, but when we will find out, then we will have to express it in liters. Going back to our formula, PV equals nRT, we divide both sides by pressure, and we find that the volume is nRT divided by pressure. Plugging in the appropriate numbers, we will have, for number of moles, 0.0548 moles, times, for the constant, we're going to use 0.0831 liters times bar over mole times Kelvin, times, for the temperature, we will be using the 313 Kelvin, dividing the whole thing by the pressure in bars, 0.75 bars. This calculation will give us our volume in liters, and the final volume will be 1.9 liters. So either we provide a substantially large balloon to hold this fairly large volume, or we will need to use a graduated cylinder that is at least 2 liters large. Again, we have to remind ourselves that the gas will be collected over water, should we collect it, because the vinegar already contains a substantial amount of water, and we need to provide some space for the water vapor that will also be generated. Other experiments that we conduct in the chemistry laboratory that have the potential or do produce gases, but those gases are not collected, involve the reaction between calcium carbonate, either in the form of chalk or eggshells, with vinegar or hydrochloric acid. Both acids are strong enough, or over time will react with the carbonate to produce carbon dioxide. That gas may be collected and quantified. However, if the process is substantially long, it may not be worth it, or if our products are more valuable than the gas that is generated, it may not be worth the effort to collect the gas that is forming.